Question 2. Figure 2 shows a capacitor of capacitance 370 picofarads, so that's 370. Pico is times 10 to the minus 12 farads. Consisting of parallel sheet 250 centimeters square. That's mean, right? So we need to change centimeters square into meters square. So there are 100 centimeters in the meter, square it, so that's 100 times 100, so that's 10,000. So this is 250 times 10 to the minus 4 meters, because obviously a centimetre square is smaller than a metre square. The sheet has a relative permittivity 2.3, which completely fills the gap between the two plates. Calculate the thickness of the polythene sheet. So we need a capacitor equation here. So we need a capacitor equation here. So we're looking electric fields and capacitors, and it's this one here that allows us to work out what the capacitance is. So the capacitance is equal to the surface area times by the permittivity of free space, modified to make it the relative permittivity of the material, divided by the distance between the two plates. So we just want to substitute in our values and rearrange to get D. So let's rearrange first. D is equal to A epsilon naught epsilon R divided by C. So D is equal to 250 times 10 to the minus 4 times by that epsilon R is 2.3 times by epsilon naught, that is on the front page of your formula sheet. There it is, 8.85 times 10 to the minus 12. And we want to divide that all by the capacitance, which is 370 times 10 to the minus 12. Okay, so my times 10 to the minus 12 is immediately cancelled. Get rid of those, it'll be easier to type in. Right, so we have 250 times 10 to the minus 4 times by 2.3 times by 8.85. That's that. Divided by 370. I've already done my times 10 to the minus 12, so I get 1.3, oh dear, well, hang on, 1.375. How many sig fig do I want it to? That's 2, that's 2, that's 2. So we want it to 2 sig figs, so that's actually 1.4 to 2 sig figs, isn't it? Times 10 to the minus 3. So that's 1.4 millimeters at 2SF times 10 to the minus 3. Let's not forget that. Okay. The capacitor is charged, so there's a potential difference of 35 volts between the plates, and presumably they mean across the plate. The charge on the capacitor is 13 nanocoulombs, so that is 13 times 10 to the minus 9. And the energy stored is 0.23 microjoules, so that's times 10 to the minus 6. The supply is now disconnected and the polythene sheet is pulled out between the plates without discharging or altering the separation of the plates. Show that potential difference in the plates increases to 80 volts. Okay, so what we need to do here is we need to look at what the capacitance here is. So capacitance is equal to A epsilon naught epsilon R over D. So what's changing if we pull the sheet out? Well, that's not changing. That's not changing. That never changed. That's a universal constant. That one isn't changing. We're not moving the plates apart, so that is changing. So we have the capacitance is proportional to the relative permittivity. So that means that the new capacitance is going to equal the old capacitance divided by the previous relative permittivity. Okay, so we've reduced the relative permittivity from 2.3 down to 1, because the relative permittivity of free space is 1. So that means we're going to reduce the capacitance. The capacitance is going to get smaller, and it's going to get smaller by 2.3 times. Okay, so V is equal to Q over C. So that's just using this equation here, which I've rearranged. So that is going to equal, well, Q was this amount here, so 13 times 10 to the minus 9, divided by the new capacitance. Well, the new capacitance will be the old one, which was 370 times 10 to the minus 12, divided by 2.3, this one here. Okay, so here goes. We have 13 times 10 to the minus 9. We want to divide that by 370 times 10 to the minus 12, which is divided by 2.3. I've put the bottom bit in brackets. And we've got 80.8, 108, 108, 108, 80.810, and that is in volts, which is about 80. Okay, calculate the energy that is now stored in the capacitor. So we need energy stored in a capacitor now. Any of these will do. I'm going to use E equals a half CV squared, because I find it the easiest to remember, because it's like kinetic energy. So a half C is 370 times 10 to the minus 12 divided by 2.3, and V squared is the answer that we just got, so that's 80.810 squared. Okay, so we square this, times it by this, 370 times 10 to the minus 12, divide by the 2.3, times by a half, and I get, just press E and G on that. Oh, I want it in microjoules, because that one's in microjoules there, that's in nanojoules. So if you press shift and then this button here, it will move it back to the next power of 3 here. So that's in microjoules now, so that's equal to 0.525 microjoules. So 0.5, that's going to round that to a 3, isn't it? To 2 sig figs. Okay, explain why there is an increase in energy stored in the capacitor when the polythene sheet is pulled out between the plates. So how does this happen? You have a capacitor, it's got so much energy on it, you remove something and suddenly it's got more than twice as much energy on it. Okay, how on earth can that happen? Well, when you pull the polythene sheet out, there is a force between the polythene sheet and the plates, because the polythene sheet has charge on it and the plates have charge on it, charge on them. So if you have a force and you move it through a distance, you do work. So essentially by pulling the polythene sheet out, you're doing work. The polythene sheet couldn't come out on its own, you have to pull it out, which means that you're doing work. So the answer to this question is because the sheet and the plates are charged, there is a force between them. Removing the sheet requires you to do work which accounts for the additional energy. Okay, so because they're charged, then you pull it out, you're doing work, which means that you can increase the energy stored on the capacitor. Right, so just to illustrate this, if we have the positive charged plate here and the negatively charged plate here, then the plastic atoms are dielectric, so they'll look a bit like this, with their negatives at the top and their positives at the bottom, etc., etc., all the way along. So that's positive, negative, negative, positive, negative, positive, negative, positive. So that's the plastic. And that is the plates. Okay, so as you pull this sheet out, you've got a negative there and a positive there. They're attracted to one another, which means that as you pull them out, you have to do work against the electrostatic force in order to pull it out. So because the sheets and the plates are charged, there is a force between them. Removing the sheet requires you to do work. I guess we could have said work against the electrostatic force there. Maybe that would be a better answer. There we go, which accounts for the additional energy. So as you pull this plastic out, negative and positive, they need to be pulled apart, which requires work. Okay.